All right, one last example of making a piecewise function continuous. This one actually has two unknown constants, so we'll have to find the value of A and the value of B. And the value of A part gets at what I've been talking about with the removable discontinuities. And B gets at another issue that you'll probably see more of in your homework problems, I believe, where we can adjust the functions so that they meet each other when your function's in two fully separate pieces. So this time we are not trying to place a single point. We have the first function for all x less than 2 and the second formula, I guess it's all one function, being valid for all x greater than or equal to 2. So the first piece again, we're trying to make ax minus 4 over x minus 2 continuous on its own. We don't want an asymptote because the function does split at 2, so that asymptote would be part of the graph no matter which direction we're splitting. If we want to think about this the factoring way, we want to be able to factor so that we have an x minus 2 on the top, which means that we'd have to factor out a 2. If we want this to distribute back in and give us minus 4, it would have to be a 2, which means that the a has to equal 2. So that's kind of working your way up to it with how you think the equation should look so that you can cancel and remove that discontinuity. If you'd like to work on this the other way, we need to make sure that we're getting that 0 over 0 form when x equals 2. So if we plug 2 in for x, we'd get a times 2 minus 4 on the top, and we'd get 2 minus 2 on the bottom. So the bottom is definitely 0. If we also want the top to be 0, then our 2a has to equal 4, which means a has to equal 2. So same answer, a couple of different ways to approach it. So that was more like, how do we make the limit exist type of question, which means that we've decided that a is 2. Okay, so first one decided. Now we need to make b be the correct value so that these two functions actually meet. So really, we can remove that discontinuity and we could say, well, this is exactly the same as if this was just 2 for x less than or equal to 2, or I'm sorry, strictly less than 2, or bx minus 4 if x is greater than or equal to 2. And again, the reason I'm saying that is because up above, if we cancel the x minus 2, we're only left with 2. With that restriction that x can't be 2, but since we've already restricted the domain of that piece to x less than 2, we can just say we always get 2 out of that for the domain that we're given. Okay, so we now need to take, and I can even give you a visual on this, we need to take y equals 2 if x is less than 2, which is a horizontal line, and we have a line with a y-intercept at -4, and we need to play with its slope, so we can imagine all these different lines with different slopes. We need to play with that slope so that it runs right in and fills in that point. So this visually is what we're trying to do. One way to do it, if you want to do it kind of the plugging in numbers way, is to say, okay, when we plug in 2 to the first piece, we're just going to get 2. When we plug in 2 to the second piece, we're going to get b times 2 minus 4, and we need those to have the same y value. We need the y's to be the same. So we can add 4 to both sides, and it looks to me like b needs to equal 3. I want to do one last thing. I want to go check this out in Desmos. Desmos is another way to play around with this. Make sure that's not the only way you know how to approach it, because if you're working on this in class, you won't necessarily have Desmos, but it is a really neat way to try and get some understanding. So we want to play, and we can even play around with that first function before we type in the second one. We had a fraction. What did we have? We had ax minus 4 over x minus 2. We can turn that slider on and we can play around with that. You see that there it is in the middle. It's when those branches finally connect. We can also put in the domain restriction. We only want to see x less than 2. So there it is with x less than 2. And again, if we go up to a equals 2, that's when all of a sudden we don't have the asymptotic behavior anymore. The second piece was bx minus 4. Oh, and I'll say y equals, but it does work without it. And I'm going to do the same. I'm just going to add a slider so I can play around. So there it is. It's always going to cross at -4. And we get to just mess with that slope until it hits right. Oh, I almost had it right. There we go. I got it. Again, if you'd like, you can put in the domain restriction. This is for x greater than or equal to 2. So you can see that we made the two pieces connect and the function no longer has a discontinuity there. So some of them are really fun to play with in Desmos, but again, make sure that you understand how to do it by playing around with factoring if you have a fraction, or by plugging in the value where you need the two pieces to meet if you have formulas that aren't rational.